this lesson, we'll be looking at turning points. We're going to look at the turning point, and we'll look at that through differentiation. Now, hopefully you know that we can find the instantaneous rate of change anywhere on this graph, or the gradient at that. One way we can do that is by drawing a tangent line to those as well. So what we can actually do, I'm just going to take a little snippet. I'm going to zoom this in actually, and now I'm going to take a little snippet of it. Okay, so we can actually draw a tangent line to figure out what the gradient is at any point. So let's have a look at this. And if we've got this in here and I want to draw in a tangent line, so what I mean by that is we just put a line on. If I want to know what the gradient was right at this point, I would need the line to be parallel to that point there, which is pretty close to that. It's probably not quite, it's probably more like that. If you're looking at this point here. So you can see that there would be my tangent line there. I'll just make that a bit more thicker. Okay, so that is my tangent line there, right? The one that goes there. So one thing that we're going to try and look at today is if I have as we come around to the turning point, as we come around more, so, you know, we can sort of move this tangent line. You can see it starts to decrease as we get close to this turning point. So I'm just going to get closer and closer to it. Just touch this and look at the tangent line to that. So as you can see, the gradient of it is decreasing. So if we draw a tangent line, that indicates what the gradient is doing. And that's sort of why we introduce tangent lines. That point is getting closer and closer. And then, you know, we're getting closer and closer, as you can see there. That's the gradient there. And you can see the gradient keeps on decreasing, right? And you can see there it's decreasing. So the gradient at that point there. And as we get to that turning point, okay, so we get really close to it. Okay, so that's probably slightly still to the left there. All right, but as we get to that turning point, what you'll find is that the gradient gets to a value of 0, because that line has a gradient of 0, like it just touches it. Remember, great tangent line that. Once you get past it, the gradient then becomes positive. Okay, again, on this case, because it is a turning point, it goes down that and it goes back up. It's a stationary point of inflection, and we'll get to 0 and we'll look at those a bit later. So the same thing occurs up here. Okay, so if we look at the tangent line for here, all right, as we're on this side of the slope, you're going to have a pretty steep line. Okay, so you can see that tangent line there would be about this point here. And then as, you know, we get up a bit higher, you can see that the gradient starts, it's positive, but it's starting to decrease. Okay, so it's a positive gradient starting to decrease. Positive gradient starting to decrease, and as you can see, you know, where it's just touching, that's matching the gradient. So as we get closer and closer to that turning point, you can see the gradient is decreasing, and then when it's right up the top, it's going to have a gradient of 0. Okay, and then it's going to start, once it goes over the other side of the turning point, it has to get negative. Okay, so you can sort of see the difference there between both sides, sort of just positive on this side, reaches 0, and then basically gets to here. Do you guys understand? My question is that at this turning point, the gradient is 0. Can you see that the gradient at that turning point was 0? That's pretty much all I need you to recognize for today's lesson. If you can understand that, hey, at the turning point, the gradient's actually 0. You can give me 0 to 5 about if you understand that. 5, yeah, that makes clear sense that at a turning point, the gradient at that point would be 0. Because the tangent line has to be that. So we know the gradient here is 0 and the gradient here is 0. If you can just do that in the chat comment, that'd be great. 2 plus 3x minus x3. Y equals 2 plus 3x minus x. 3. Okay. Let's see how we're going. Excellent. Fantastic. Great. All right. So my next thing is then, how do we find the turning point of cubics? Because that's what we're going to find. So we know how to find intercepts steps, because we found the factors of those, but how do we find turning points? Well, all I need to do is find out where the x-coordinate is, when the gradient is 0. So to find these, I want to find the x-coordinate when the gradient is 0. If I can find it there, it's going to give me 2 points. The gradient's 0 here, and the gradient's 0 here. I just want to find out where the x-coordinate is when the gradient is 0. And that will tell me. Now, if you go back to calculus, calculus shows us the rate of change. So if we actually differentiate this equation, I get an equation like this. This graph is going to show me the gradient values. Remember, it really shows me the gradient values. Now, you don't write this, but this is just my thinking. For each x-coordinate, gradient values for x each coordinate for the graph of y, or could be fx if it's written like that. So it's showing me the gradient values when we differentiate for each x-coordinate for the graph of this. So if I put this in, 3 minus x squared, 3 minus x, squared, we get an equation like this. That's dy over dx. Okay, which is really what it is there, but I'm just going to put it in as y, and that is the calculus. So if we look at this graph, what this has shown me is a couple of things. Now don't forget, when we differentiate it, it shows me the gradient at that point. So let's have a look at something. The concept is all you need to understand, because the math you already know how to do. So it's just about getting across how this concept works, and then you'll be able to understand that. Okay, no, I don't. I just want to change the color to red. That's all I want, just a plain red. It's orange, apparently. This one will do. Red. Okay, so if we're talking about the tangent line, at this x-coordinate, you can see that the gradient of that is pretty negative at x equals 2. As we come around a bit more, hang on a moment, what do I do to the equation? Hang on, I don't think I put that in right. Did I put that in right? Whoops, sorry, I stuffed that up. That should be 3x squared. I didn't differentiate that correctly. Working out, I should have had that as 3. There we go. 3 minus 3x squared. Sorry, I do apologize. 3 minus 3x squared, that's better. I'll take a snippet of this one. Make sure you differentiate your equation correctly. If not, you're not going to quite get it. All right. Yeah. Okay, we have this equation here. This is my tangent line. I have to make it green now. Okay, so what this does is this will actually show me the gradient at all these points. So if I come around and let's have a look at the gradient value approximately, at this point here, okay, here, right here. I'm going to try and match that up, and we're going to try and calculate the gradient just by drawing an approximate tangent line. That's pretty good. I like that. That's pretty good. That's not a bad approximation of tangent line. Now, if we extend this a bit, Now, if you look at this gradient, we can calculate the rise over run, right, to figure out what the gradient is pretty much at that point. So we've got, what's that, 2.5? You might as well say 2.5 over a half. Oh no, that's over 1. So it's got a gradient of about, rise over run, it's got a gradient of about what, negative 2.5. And if you look at this point on the original function, it's got a gradient of probably about negative 3. I think, hang on, no. Yeah, that's over 1. Sorry, it's got more than 2.5. Is it about 2.5? 2.5-ish. Yeah, it is about 2.5 over 1. Maybe a bit more, 2 3/4. But as you can see, the gradient's pretty close there to that. Now, as we move around, you can see that the gradient is negative, and as we move around this, it gets less and less negative. Okay, so you can see that the gradient is getting less and less negative. So if we see at this point, you can see it's less negative. Hence, the coordinate of the derivative graph is saying what the gradient is at that point. It's negative. As we get closer and closer to that turning point, the gradient now at this point, so let's just get a gradient of 1. Let's try and just see where the gradient of negative 1 is. That would be negative 1 there. So the gradient of negative 1 is about there. So if you look at that, see how that has a value of negative 1 there? That's the point of negative 1. Then as we come to a gradient of 0, well, that's going to be on my turning point. Hence, and just by coincidence, it actually intersects there. That's why I chose this graph, is that you can see that the gradient at this point is 0, because this is showing the gradient for each of these x coordinates. Then, as I go past that point, let's try and find a gradient of 1. I'm just going to make a gradient of 1 again. A gradient of 1, the tangent would be about here. So it'd be about that point. You can see here has a value of 1 at that x coordinate. And then we get steeper and steeper, okay? The steepest part we get would be, where is the steepest part we get? The steepest part we get on this graph, it's probably a bit steeper. Let's find the steepest part of this graph. You can see that the steepest part of this graph is right here, which is why that's the turning point. So that's the steepest part of the graph. And then after that, it actually starts to get not as steep, okay? So as you get past that point of inflection, you can see it starts to decrease as you come at the top there, okay? And then again, it starts to decrease its gradient, starts to decrease its gradient. And then you're going to get basically, it keeps on decreasing, as you can see. So if you think about it like a car driving on it, right? Like if you think of this as like a roller coaster, like, whoa, you've got a really steep gradient, steep gradient, steep gradient, whoa. And then the gradient like doesn't get as steep, so it's a real negative, and then it gets less and less steep, hence why this line comes up. And then it gets to a flat, which is 0. And then it actually becomes a positive gradient. You start going up, hence this now starts going up. And then you go up, up, up. This is as steep as it gets. Then it actually is it's still steep, but it's not getting as steep. So that's the steepest part you reach here. And then it starts flattening out a bit. So it's still got a positive gradient. This is still in the positive sections, because this is saying, when we're looking at the green graph, we're saying the green graph is showing the gradient value of the blue graph. So we're trying to say that at this point is the steepest point. It's still positive, the gradient here, but it's not as steep. Then when we get up to this point, the gradient is 0. And you can see there, the gradient is 0. Then when we get down past this point, the gradient, you know, if you're on a roller coaster, the gradient starts to get less steep, it gets steeper and steeper and more negative, okay, as it goes. And it keeps on infinitely, you know, getting steeper and steeper. Hence why this drops away so fast. So the green graph shows me the gradient for each of these x coordinates, and they both match under each other. So here, the gradient has to be 0. From here to here, the gradient has to be positive, because the gradient is positive here all the way. As we can see, we're in the positive sections. This section, the gradient's always negative until it hits 0. So as you can see, the gradient's always negative until we get to 0. And when we get here, then it becomes a positive gradient. And then when we get to here, it gets to 0. And then beyond that, the gradient becomes negative. So this derivative graph shows me the gradient value for each of these corresponding x coordinates. So they both share the same x coordinates. Does that make sense? 0 to 5, if you kind of understand that. And if you understand that, then it's just plugging in one bit of information, which is the math. Give me a bit of feedback on that. That would be great. Okay. Excellent. Okay, I'm going to move on. So what we realized is that this was our original graph, the blue graph. This is our derivative graph. The derivative graph shows me the gradient values. So to find the turning points of the original blue graph, I just need to find out the x-coordinate. When is the gradient 0? To do that, basically, I derive it, and then I want to find out, hey, when is the gradient 0 in this? So remember, this is showing the gradient values. So what I do is I let dy on dx equals 0. And this is just my thinking, by the way, guys. You don't actually write that. Okay, this thing's just my thinking. And I'm going to do my thinking as well. Why I do this is as I want to know the x-coordinate when the gradient is 0. When the gradient is 0. So that's why I'm letting it equal 0, okay, for this section. So I let it equal 0 because as I want to know when the x-coordinate, I want to know the x-coordinate when the gradient is 0. So I let dy equal 0. So I'm saying, hey, if the gradient equals 0, where does that occur? Well, this is now we can factorize this, right? Or you can solve it using all the knowledge that you know about quadratics. So we're just going to make it 3x squared equals 3. Divide by 3 on both sides. X squared equals 1. X equals plus or minus the square root of 1. Square root of 1 is 1. Therefore, x equals -1 and 1. You're telling me the gradient equals 0 at x equals 1 and -1 and 1. Let's have a look at that. When we derived it, well, yeah, look, it's -1 and 1. So that's where the x-coordinates are that. Now we want to find the turning points of the actual graph. So I've then just got to substitute these x values back into here to find the y-coordinates. Therefore, sub x equals -1 and 1 into y or f of x to find the turning point coordinates. Okay, so I want to find the coordinates. So really, because I know that at these points the gradient's 0. So therefore, I'm just going to substitute it back into my original graph, which is y equals 2x plus 3x minus x cubed. Y equals, was it 2x? It was 2, I think. 2, yep, plus 3x minus x cubed. Okay, so I'm just going to sub in 1. So we've got y equals 2 plus, 3 times 1 minus 1 cubed. Y equals 2 plus 3 minus 1. 5 minus 1 is 4. I'm also going to sub in then -1. Y equals 2 plus 3 times -1 minus -1 cubed. Y equals 2 minus 3. -1 cubed, negative positive, still be a negative, but a negative will make it positive. So that's in plus 1. So y equals 2 minus 3 is -1 plus 1 is 0. So we have a couple of coordinates here. Oops. So that means Is that not? So what we can realize is that, just fix this up, sorry, that was, so what we found is when I substituted in 1, because I knew it had a gradient of 0 at x equals 1. If I substitute it back in to find the turning point, I know that the turning point is, well, I know it's at 1 when the gradient is 0 for x, and I substitute it back into the original equation, I know what happens at 1, 4. And I also know that when I substitute in -1, the y-coordinate was 0. So I know the turning point is at 1, 4 and -1, 0. So my turning point is at here, 1, 4, and this was at -1, 0. And that is the math for the basic concept. So let's just have a think about that and review that again. You've got an equation. We can derive it. When we derive it, it shows the gradient of each of these x values. So if I want to know the turning point has a gradient of 0. I know here, at this point here and this point here, the graph has a gradient of 0. Look, it does. And that's where the turning points are. I use my quadratic information to find out where those x-intercepts are. I find out that that's actually at -1 and 1. I then substitute it back into this equation to find out what the coordinates are. When I substitute in -1, I find out y equals 0. When I substitute in 1, I find out the turning point's at 1, 4. That's all we're doing, guys. Another thing I know is I know the shape of this. Because of this graph, because I know it's an inverted parabola, I know the gradient on this side is negative. And I know here it's positive, and then it goes to negative. So I know that the graph starts off. So I know that the turning point is at, just by thinking about the turning points, I know that when I substituted it, I have a turning point of 1, -1, 0. And I also have another turning point of here, which is 1, 4. Now, if I had to draw that, it also confirms with me that the gradient before that is 0. So it has to be, sorry, is negative. So it has to be like a negative gradient. So it can't be coming from this direction because that's a positive gradient. And because this is a turning point, that needs to be negative coming down here. And then at this point, it changes to a positive. So that means it has to turn up this way, which makes sense. Halfway between these 2 points is my point of inflection. So it's going to get steeper and steeper and steeper and steeper and steeper. Here at the turning point, it's actually still going to be positive, but it's going to get less and less and less and less steep. Okay, until we get to this point, then the gradient will hit 0. So it's getting less and less and less and less steep. I'm still a positive gradient though out here, and then we get to 0 gradient. Then after here, it starts to get negative. Well, to go negative, once you hit here, at that turning point, well, it has to come back down and it's going to get steeper and steeper and steeper and steeper. Okay, and that's how I can determine what the shape will actually look like just from looking at the derivative graph. I'm going to run through another one of these just a bit quicker to just bring it together. If you can give me, while I set this up, just your feedback on how comfortable you feel about that, that would be great. Yeah, that's super clear. I find this pretty easy. Or what? I completely lost you. 0. I've got no idea. And I really don't mind where you're at because I can explain it different ways. All right. Awesome. Okay, so I'm going to look at this graph here. Okay, so what I want to do is find the turning points. We're not talking about the x-intercepts because we already know how to find those. That's where we try and find a factor, and then we do long division, and it tells us where these points are. From this equation, I can also see that the y-intercept is at 11. Okay. The last thing we need you guys to plot is the turning points. So we have done these cubics before. We haven't talked about the turning points, and that's where I'll say, hey, we'll use calculation differentiation. I know the turning point at this point is going to be 0 and 0. But just say you're given the equation and you didn't have a clue about it, you didn't have a CAS, and you're just told to find where the turning points are. You probably have to graph it all, but we're just going to focus on turning points today. The first thing I'm going to do with this equation is I'm just going to get my equation, and let me just start a new page. Sorry. Okay, I'm going to write that down. So we've got the equation is y equals x cubed minus 3x squared minus 9x plus 11. I know the gradient should be 0 for the turning points. So I'm going to derive it and get my gradient graph. I like to call it gradient graph just because it shows me the x coordinates of the gradient. I shouldn't talk while I'm trying to do maths. 3x squared minus 6x minus 9. That's my graph. I want to let dy on dx equals 0, which is really saying, hey, if I let it equal 0, I want to find out when the gradient's 1. If I let this equal -2 or -3 or 4, I want to then find out when the gradient's -2 or the gradient's -4 or when the gradient's 2. Here, I just want to know when the gradient is 0, because if the gradient is 0, that's my turning point, because that's where my tangent is. So now I solve for this. Now, in this case, now I just use my quadratic squirrels. I'm going to take out a common factor of 3. Always take out common factors. Much easier now. I can divide both sides by 3 if I want. It really doesn't matter in this case. So that's going to be x, what are we looking at? Minus 3 plus 1. Therefore, x equals 3 and -1 is where the gradient, this is just my notes view, equals 0. Okay. Now I know that it's at 3 and -1. Now I can come back to the original equation. It was -3. It was 3 and -1. I want to know the coordinates of the turning point. This is the x coordinates where the gradient's 0. Okay, 3 and -1. -1 and 3. But it's not telling me where the coordinates of the turning point. So I've got to substitute them back into this equation and find out what it is. So it should be -116. Substituting there, 3, it would be -16. So if we sub them in to the equation, we'll get y equals 3 cubed minus 3 squared minus 9 times 3 plus 11. This worked out really well because I don't even need to figure out that's 27 because that's 2 3 3s. That just equals 0, which is 27 minus 27. 9 times 3 is -9, 18, 27. -27 plus 11. So y equals, what are we looking at? -16. Therefore, the coordinate of the turning point is at 3, -16. Also, the gradient was 0 at -1. Sub it back into the original equation. I just can't quite see it. This one here, just subbing it back in, just to find out where the y coordinate is, because I know the gradient's at 0 at these two x coordinates. What's the y coordinate? Just ran out of room. Plus 11. I'll just move across a bit. Plus 11. So I've got y equals -1. That's going to be +1, but -3. So that'll be -3. That'll be plus 9. Plus 11. What do we got here? We've got 20 minus 4 is 16. So therefore, we have the coordinate of the turning point. -1 is when the gradient's 0. I've substituted it back into the original equation. 16. -1, 16. So I know on my graph that would be it. Also, another thing I know is this is a positive derivative graph. So I know my derivative graph is going to be something like this, right? And it's going to be like a, this is -1 and this is 3. What I know about my graph is it has a positive gradient, has a turning point here, negative gradient, turning point here, positive gradient. So I'm at negative 116. So when I draw this, I'm at negative 116, and at 3, it was at 3, negative 16, right? So this is negative 116. And then we're at 3, negative 16. So it'd be like, that should be roughly the same distance. Should be that there. And if that's 1, it should be 1, 2, 3. So notice I've kept my scale pretty good, so it should be about there. I know that is 3, negative 16. Now looking at my derivative graph, it has a positive gradient up to this point, and then it goes negative. It has to come from this way. Positive gradient. And then it goes here. It can't come this way because that would have a negative gradient, right? It has a positive gradient before that because this, just from looking at the equation of the parabola, the derivative graph, which was 3x squared minus 6x, we know that that's a positive graph and we have the two intercepts. So I know it has to have a positive gradient. So it has a positive gradient, then it goes negative. Oh, well, that makes sense. It's going to go negative, and I know that the y-intercept is going to be at 11. Okay, so I know the y-intercept is going to be at 11, so it's going to be around here-ish. So then it's going to go positive, and then I know that halfway, because we've got, if you think about it, that'd be 2. We know here would be the turning point at 1 something. So I know at 1, that should be my point of inflection. So really, it'll be, I've probably stuffed this graph up already. It should probably be coming more in like this. Hitting here, 0, going through 11, getting steeper and steeper and steeper. Oops, I've probably stuffed it up. Getting steeper and steeper and steeper until I hit this point, and then it'll be getting less and less steep. But mind you will find your x-intercepts as well, which will help you. And then it's getting less and less and less steep, but it's still negative, and then it's going to hit 0. Okay, so we know it's came in. Ignore this. We know it's came in as a positive gradient. This is positive gradient until it hits this point, and then it's gone negative. And the steepest point it's going to occur would be at 1, because that's a point of inflection, and then it starts to come back to 0, and then it goes positive again. It's going to go back out. Okay. Now we could, and what you will end up doing is you'll end up finding where the x-intercepts are of this by trying to find a factor. Okay. And then when you find a factor, because you can see that a factor of this would be 1. If you put 1 in here, it would equal 0. So we can actually do this. Why don't we just do the whole hog? And this is where you'll be bringing it all together in these later chapters. So I know if I substitute in 1, so that equals 0. Therefore, I know that we've got x minus 1 is a factor. Then you can do long division, you can do your box, or you can do it by inspection. I'm going to just do it by inspection. X minus 1, that has to be x squared. To get 11, that would have to be minus 11. Okay. Negative 3x squared, that's going to be negative x squared. I need another 2, so that has to be negative 2x to give me negative 2x squared. I'm going to check with negative 9x. So that would be 2x positive minus 11x. So that's correct. So I know that's what my equation is. Now, can I derive this? Not off the top of my head. So I'm going to have to put that through the quadratic formula to complete the square. B squared is 4 minus 4 times 1 times negative 11. So that's going to be 40, negative 44, 44. That's going to be 48 is my discriminant. So my quadratic formula, I'm running out of room. No, I'm not. That's good. Is, what is my quadratic formula? It is minus B plus or minus the discriminant on 2A, I believe. Correct me if I'm wrong. I think I could be wrong. So therefore, B is, what was B? B is negative 3, so it's going to be 3 plus or minus root 48 on 2. So root 48 is just a bit below 7. right? So it's like 6 point something. So I'm going to just treat it as 7. That's going to be 10 on 2. So that's going to be just a bit below 5, right? So it's just slightly below 5. So it's like maybe 4.99. And if it was 3 minus 7, that would be -4, but slightly, not -4, it's like negative, because I would have minus 6 point something. So I say it's -4, so it's like -3 something. So that's just a bit below, I say. 3 minus 4 is 7, is what I'm thinking. 3 minus 4 is 4 on 2. 4 on 2 is 2, right? So it's pretty close to 2 as well, to -2, I should say. So then I know that I can put my coordinates in for here. I know that's going to be, hey, it does go through there. 1, 0, 1, 0. I know that this is going to be 3. This is going to be 3 minus square root of 48. I can take 8 out of that. I haven't simplified that. Should simplify that. 48 has 4 and what have we got? 4 times 12. 12, and that has 4 and 3. Can't do that, so it's going to be 4 root 3. 4 root 3. Okay, so that's 4 minus 4 root 3. And I think it was all on 2, wasn't it? On 2, yep. All on 2, comma 0. And this one is 3 minus plus, sorry. And notice it would just be before 7 if I had my scaling. 4 root 3 on 2, comma 0. Okay, and that's how you can actually graph your graph correctly. And that's where you'd go all together, so using information. The main thing I really wanted you to take away from today's lesson was to understand the concept that when we're deriving these graphs, if you have this graph, when all you need to do first is do the derivative of that. Once you do the derivative of that, that shows me the gradient at any point. I then want to find out when the gradient's 0 for this derivative. So I let that equal 0, the equation, and I factorize it. Then I find out where the x coordinates are. Here, here. So I know it's got a gradient 0. X equals -1. Look at that. And x equals 3. Look at that. I know that it's going to be positive gradient, 0, negative gradient from here to here, which makes sense. This is all negative from there to there, and then positive gradient here onwards. Once I've found where my x coordinates are, when I know it's -1, I substitute -1 back in the original equation, and that'll tell me the coordinate is -1, 16. I know that it's also got a gradient of 0 at 3, so I substitute that back into the original equation, and that will tell me at 3, the turning point is at 16, -16. And that's how we get there. Hope you enjoyed today's lesson. I really enjoy it. I think it is absolutely fantastic.